when it works alone, so actually the real power, reactive power, we supplied by the generator will be fixed. And so means that if we have a 1,100 kilowatt of a generator, so the 1000 kVA, let's say, and for generator it will produce in terms of volt ampere, because it has a lagging power factor or leading power factor. So we shall represent in kVA, and means that 100 kVA not supposed to be 100 kilowatt, maybe just around 80 kilowatt of power. So this 100 kVA, if we look from our trigonometry point of view, so this kVA is the apparent power. So it was consist of P and Q element. So means that our S squared is equal to P squared plus Q squared here. So this 100 kVA represent the S. So the real P and reactive power supplied by generator will be fixed and is constrained to be equal to the power demand by the load. Means that how much the load can get from the generator is depend on the generator limit itself. You cannot get or drain out more than this 100 kVA or amount of power, real power and reactive power that remain inside our generator. Meanwhile, our frequency and terminal voltage can be varied by the governor set point and the field current, like we have learned before. We have our VF, we have our generator, RA, XS. So we have our V terminal. So the output to the load from this V terminal in terms of their frequency and voltage will be varied by the governor. Frequency will be controlled by the rotation frequency of our shaft. The faster the shaft rotate, the higher the frequency will be. And we providing or supplying an AC source to the load. So this is an AC generator. Meanwhile, the intensity or the amount of current that delivers to the load or draw by the load can be enhanced or can be controlled by the intensity of our VF here. So the higher the VF, means the more the current that we can deliver to the load. So if we put load here, it draws current. If we increase the load, so the voltage tend to drop. So how to increase the supply voltage? So we increase the amount of VF and or increase the amount of IF. Okay, isolated synchronous generator supplying its own load independently. It's very rare. Means that one generator to supply the whole load. So it is applied, but very rarely applied. Means that one generator. So we have many load connected. So this is very seldomly being applied. So we have, let's say, we have 4 motors supplied by one generator. So why? Because if anything happen to the generator, so all the load will be affected. So it is not so preferable to be applied. And is that one generator supply many load. So this is what happen. What happen if generator is failure or under maintenance. So you cannot use all the load. So by right, all generators are driven by the prime mover. So when you turn this prime mover, it will produce 3-phase output and 3-phase output. If single phase, but usually the generator for synchronous machine are wounded in term of 3-phase, red, yellow, blue, and 3-phase. So the higher the number of poles, so the lower the speed you need to put in to generate the certain voltage of output. So that's presented by the poles number. So all the generators are driven by prime mover, source of mechanical power, either from steam turbine, water turbine, diesel engine, and etc. And might be before the shaft. If let's say the incoming turn is too low, so we shall have a gearbox, and we shall have a gearbox either to increase the speed at the shaft or decrease the speed of shaft. So we have gearbox here, and so let's say we have a slow moving but high force of power, so we better put a gearbox to increase the shaft rotation before we feed into the generator. Okay, that's for slide number 3. Okay, next. What happened, or what is the advantage of when we run the generator in parallel operation, just not in single or standalone mode, but now in parallel. So parallel means that we have a few generators. So we have a bus bar, we have a transmission line, but over here maybe we have a 2 or 3 generators in parallel. So here we have a load, we have load motor, let's say. So 2 generators connected to one bus bar, then transmit to another end. Then at the end of the transmission line, we have another a series of load. Okay, several advantages. What are the advantages when we put in parallel? It can supply a bigger load than one machine by itself. Let's say we have here 100 kVA. So this also 100 kVA. Maybe another generator of 50 kVA. So means that now we have already 250 kVA in line instead of single generator of 100 kVA. So we have now already 250 kVA. So bigger load can be connected at the end of this transmission line. And also it can increase the reliability of the power system. Let's say we have a failure on this generator and this generator, so we have another one that on operation. Okay, means that we are able to perform maintenance or bear any kind of disruption during the generation, because generator, when we focus on generator at industry, the generator actually will work 24/7, not only 5 times a day, few hours per day, but when we talk about big generator like this, it will work 24/7, 24 hours, 7 days per week. So it means that sometimes it has to perform. We have to perform periodic maintenance, servicing on the generator. So we cannot just take off all together. So we have to do one by one. Maybe let's say we are performing maintenance on this generator, another 2 in function. Maybe this is on the service, another 2 in function. So we have to plan the maintenance, the PM, preventive or annual or 5 years maintenance. Okay, it allows one or more to be removed, shut down, and PM, preventive maintenance, not private message, preventive maintenance. If one only generator used, not operating near full load, then there will be a relative efficient. So means that if you have here 100 kVA and here 100 kVA, but at this time, maybe the load is under maintenance, the load itself under maintenance, so the remaining is 50 or 40 kVA. Okay, means that if you have here only a 40 kVA load, you have 40 kVA load. So it is not a wise decision that we off this one, but we on this one with a 50% of operation or 50% of power range and power rating. Means that we are working this generator at 50 kVA. It is not a wise plan or strategy, because once you reduce or operate the machine below its rated current or rated speed, rated current, rated power, so the efficiency will drop. So it's better, or it is a preferable option that we run this one. At the meantime, we off this one, run only the 50 kVA synchronous machine or generator to cover the 40 kVA load. So it means that it runs almost at full rated power. So this one is more preferable strategy. So one generator needed, so you use the most which is can run at its full power rated power. Faham tak? Ada tak faham tanya? So I believe the slide that I shared with you all before regarding the paralleling of generator system, basic of synchronous machine, we have viewed before, so we don't have to run here again. And all the slide that I shared with you all by right, you should see on, because it shares the information that I will not repeat again unless you ask me, whichever you don't understand, you still have a blur information on it, so you can ask me and I can explain again. But if not, we shall proceed directly. Okay, so far any question? Can hear me clearly?
No, sir.
Okay, thank you. Okay, synchronization. The condition we have to comply before we parallel the generator. Required for paralleling. Pening nak sebut. So if we have this generator, let's say G1, so the curve maybe like this, and we have a G2, so the curve also should be the same as the above G1. G1 and G2 have to have a same magnitude. The magnitude should be the same. So the voltage should be identical in terms of their RMS magnitude. And also have the same phase, means that if it starts at 0 degree, so this one also should start at 0 degree. Same phase. What happens if you have a different phase? Let's say this one start at 0, meanwhile this one start at 90 degree. So it means that this generator actually it will not supply the line. Instead, it will supply to the G2. It will charge G2. And because when this one reach already 90 degrees, or let's say we have a 400 volt generator, this one already reached 400 volt, this one still at 0 degree or 0 volt. So 400 volt will go into the 0 volt line and will damage the generator. And it will charge, and then this one will charge the other generator. So charge and discharge will happen on the G1 and G2, and instead of supplying the line, it will charge and discharge the generator itself. So it will damage the system. Okay. Means that a huge current will flow into the unequal phases. And also the angle of phase must be equal. So when supplying from the three phase, we have phase A, phase B, and phase C. So let's say generator 1 is flowing A, B, C phase. phase C also, phase B, generator 2 also have to have the same phase of A, B, C, not B, A, C. No? If BCA is still okay because same phase, BCA and ABC is the same. But if you interchange these two poles, it becomes BAC, so it's already inverting the sequence. So it should be ABC. This one also should be ABC sequence. So the angles must be equal. And also the frequency of new generator. Let's say we have G1 in action, then G2 to top up. G2 to top up the line to come after G1. So means that your G2 have to have a slight higher frequency than G1. So it's just like when you want to, you have a car or you have a motorbike, and you have a motorbike. Rosak tengah jalan eh. So your friend want to push you on the back. So it has to come at slightly higher speed compared to your speed. Then it only can reach you. If your friend comes at slower speed, so it will never reach you, and it will never reach and pull you or push you to the front. So it means that the incoming helping machine or generator should be at higher speed frequency compared to the initial speed of the initial machine. Get me or not? So here it's stated over here, if the frequency are not equal, so when they connected together, the large power transient will occur until generator stabilize at common frequency. So this will happen in electrical circuit. If let's say your frequency here is not equal, so instead of it helping the G1, it draw more current towards G2 itself. So the G2 will reduce in terms of their speed and frequency, and it will drag also the G1 into the situation. We might able to simulate the scenario or event during simulation, and in lab 6, if I'm not mistaken. Okay, the list here summarized in terms of the steps to be taken during process of synchronization. Before you synchronize, so this is a process. We have G1 in action, G2 to come in. And so this is our prime mover, PM is prime mover. It rotates the G1 and is applying the load to the load, and G2 to comes in to help PM G1. So what happens is that assume G1 here supplying energy to the bus bar. So incoming G2 to be synchronized with the G1. So what happens is that we have to feed this G2 until the desired frequency, voltage adjusted equal to G1. So your frequency, voltage should be at equal of G1. And the three-phase voltage of this G2 also must be in phase. So your phase also must be at the same ABC as G1. So to accomplish this kind of, to confirm this kind of parameters, which is already comply or not, so we have to use synchronization length. This is the simplest way to check the relationship. So 3 parameters should be confirmed before we switch in or switch on this S, which is frequency has to be, it comes with a little bit higher, but it should end at the same frequency of G1. Voltage, and voltage should be at par, and your phase should be at same sequence. Okay, these 3 parameters should be taken into account before we switch on the synchronization, F, V, and phase. So in terms of active and reactive power, it shares between the parallel generator. When the generator is loaded, the power will be withdrawn from the mechanical system. Then the generator will apply the torque in opposite direction of motion of the mechanical system. As a result, the generator will slow down and the mechanic will slow down the shaft we have here. So this is V out or V load. This is the rotating shaft. So when we supply to the load or we connect to the load, so the current will be drawn. Actually, the load will draw the current. So power is drawn. So when it draws the current, the voltage tends to drop. So the voltage tends to drop, and also the speed will also decrease. Speed also will decrease. So the generator tends to slow down the mechanical system. So by changing the mechanical speed, if we change this speed higher, it is not desirable. It's not preferable because change in the frequency of the induced voltage. We can change the speed, but when we change the speed, the frequency also will change up or down. So we rather it is better to fix or make the frequency static or stable, fixed at the rotation speed as initially we put or we set, but we use governor to make the change in speed predictable with the power changes. So the governor will control in terms of their speed, is it going to be reduced or not, or fixed, such that we are not alternating in terms of their frequency here. So because the three elements, which is frequency, V out, and our phase, this is the three main elements should not be amended during the operation. Stand alone or during parallel session. Stand alone, the phase is not so critical. But when we are operating in parallel operation, so we have to take care of that. Okay, next on the house diagram. House diagram of our parallel generator. So the governor or the speed limiter sets the no load speed and control the reduction of speed, so such that the frequency and power relationship. So here we plot the frequency versus power is linear. So the best is that the frequency versus power curve is linear. We might have a curve like that, or we might have a curve like that. So this is unpredictable curve. So the governor function is to make sure that the curve is linear. Means that the response of the changes here in terms of frequency, how much it reduced when we increase the power, so the reduction should be at predictable values or linear time. So that's the governor function or speed limiter function. Okay, if the frequency generated voltage is too low, the frequency can be increased by increasing the no load speed of the mechanical governor. So it means that we will shift the whole lines here upper. If we found out that at no load voltage, the speed frequency at no load is too low, so the whole house diagram here should be increased. We cannot just increase at the no load point whether the full load is still here. So you might have a slope that differently or a different slope. And so the whole house diagram should be increased. So that's the purpose of controlling the governors here, or increase the voltage. So the node speed should be increased. Okay, we have here speed versus power, frequency versus power. Same goes to the speed. The speed also will reduce once we increase the power from no load, P at no load, up to P at full load. When we increase accordingly, the speed also will tend to decrease. So how much in terms of their decrement? So we have learned in our DC machine in terms of voltage regulation, in terms of speed regulation for motor. So in terms of induction synchronous machine, so it is mentioned in terms of speed drop, not speed drop, speed drop. So this is a uh, correct term, speed drop. So speed drop is defined by the speed that we have during or we measure during no load, which is higher. Then we put the load up to the full load. How much it reduced? Divide by the no load, the full load speed times 100%. So this is the speed drop. Means that the curve of how much speed at no load, how much speed at full load. So divide by full load times 100%. So this is the speed drop. Or we can calculate by minusing the frequency from no load, go to full load, then divide by full load. So this is the speed drop curve or trend of a standalone induction synchronous machine. So the range of the normal or generic speed drop in the market is between 2 to 4%. So all prime mover tend to behave similar, which when the power increase, withdraw from the system increase, so the speed will decrease, non-linear. So means that in real situation, the decrement will be like this. It's not a linear, but a non-linear kind of trend. So we are applying the governor connected to the prime mover to assist such that we are able to produce the linear kind of response speed drop. Okay, that's the speed drop. Then P generator, the power generated from the generator system can be defined as SP times frequency at no load divided by frequency of the system and frequency of the system. So S here is your slope, which is quoted in kilowatt per hertz or megawatt per hertz. So total generated power is your slope, which is delta P divided by delta F. Delta P means that the power that generated during no load minus power at full load. So no load is 0. So that's why we have here only P at full load. Divide by the frequency that we measure during no load minus the frequency that during full load. So this is our slope. So P generated of the system or of the generator can be defined or calculated from the slope times frequency at no load divided by minus frequency at your system, how or where it's stabilized at, or the system that we set system frequency 50 hertz, 60 hertz, and in Malaysia we have a 50 hertz system of frequency. Okay, the effect of change in terms of terminal voltage with a reactive load is that when we change the Q, we have P, Q, and we produce S. So when we change Q, or when the load draws more Q, so what happens is that the V at no load also will tend to decrease. V no load, V at our terminal lah. V at our terminal will tend to decrease. So increasing the inductive load reduce the terminal voltage. The terminal voltage is our V out or V at load terminal. Reduction of the terminal voltage can be compensated by increasing the no load voltage. So from the equation, we have done before EA equal to V phase plus IA RA plus IA XS. So what happens if our terminal voltage drop? So if terminal voltage drop, so to increase the terminal voltage, so we have to increase EA. Yeah. And we have to increase EA, so we can increase this V phase. So EA is our internal generated voltage. The no load during no load. In standalone system, power and reactive power draw from the generator are determined by the load. So as I told you before, we are not supplying the load, but instead the load will draw the current from the system. So when we put a generator to the load, actually the load itself will draw the current. So we're not delivering, but the load itself or the motor will draw the current from the system. In terms of P, in terms of Q, let's say we are having inductive, so we draw Q. We have capacitive, and it supplies Q. We have resistive, so we draw P a lot. We will see that the parallel operation that demand or generate in parallel system can be controlled independently of the load requirement by adjusting the mechanical governor and excitation voltage. So by exchanging the EA or mechanical governor. So when it operates alone, real and reactive power supply by generator will be determined by the load, governor set point. We'll control the operating frequency, field current. We have just before IF. We control the terminal voltage. So the governor will control the frequency. The terminal voltage will control by the IF. So let's say two generators are connected together. We have G1 and G2. So if we plot G1 House diagram in terms of frequency versus power. Frequency versus power. So frequency versus power. So we have this kind of House diagram. So this is our frequency at no load, frequency at full load. This is for our generator 1. Then generator 2, if we apply or put in parallel, so we can use another axis to plot the P2 House diagram. So that's why you have here P1 House diagram plus P2 House diagram. It might have a different roof level because the frequency at no load might be at different values, because not all generator comes with specific or exactly the same parameter. It has to have some sort of difference, but later during operation you have to regulate such that both are emitting the same parameters in terms of voltage, frequency and phase. But initially especially when we buy from different manufacturer brand. So for sure it comes with a different kind of level in terms of their house diagram. No load frequency, no load frequency of generator 1 for sure will not the same. And the slope also, it might have a low slope, it might have a high slope like this. So both are not the same, but at the end of operation, when parallelization, so both have to accomplish or achieve the parameter or requirement that we mentioned in terms of voltage, frequency, and phase. Okay. Get me or not? Boleh faham? Okay, let's say we have this G1 and G2 parallel over here. So what happens that total power that delivered to the load, let's say we need total of 100 kilowatt. P is kilowatt. We need 100 kilowatt. So let's say we connect to the load and we have G1, we have G2, connect to the bus bar, the transmission line, and we have a lot of motor here. So the total motor will be 100 kilowatt. So might be that G1 is rated at 150 kilowatt, G2 may be at 100 kilowatt. So the house diagram might be like this. So in terms of frequency versus power, like this. Means that when we put them together, so at the same frequency, so our settings now is the frequency. So frequency should be the system frequency. So this is our system frequency. At this system frequency, it might be that P or G1 able to supply only 30 kilowatt. Meanwhile, our G2 able to supply 70 kilowatt. If we follow the loop here. So that's why we have a small space here compared to larger space of G2. Because at this frequency, it will set the generator to supply or able to supply only at 30 kilowatt. Meanwhile, at this frequency, system frequency, this G1, G2 are able to supply up to 70 kilowatt. So you get me or not? So the most important is that the system frequency must be accomplished or must be followed. So P total is equal to PG1 plus PG2 even though we have 30 kilowatt from G1, 70 kilowatt from G2. Let's say if our capability of G2 is lower, means that the no load frequency is almost 60 Hz. Our requirement is around 60 Hz. But the no load frequency of G2 is already almost 60 Hz. So means that the sharing might be like this. So it might end up that G1 is supplying 90 kilowatt. Meanwhile, at this point of frequency, G2 are able only to supply up to 10 kilowatt. You cannot supply more because if you supply more, the frequency will drop. Let's say if you want to plot here such that the G2 supply more, so it will end up over here. So the frequency is no more 60 Hz, maybe it goes down to 50 Hz and go down to 50 Hz. So the frequency already changed. So we cannot accomplish or follow or stick to the rules that the frequency should be at 60 Hz. So if we want to share more from G2, so the frequency will be amended. Terpaksa jatuhan. It cannot be done. So that is the concern. of parallel in terms of frequency when we absorb P from the system. So let's say if we in terms of calculation, how much the power? Wait, Okay, how much the power draw from the load, the generator G1 and G2 here? So P load is equal to G1, PG1 plus PG2. But PG itself is equal to how much the slope times frequency at no load minus frequency of the system. So it means that when you this number 2 here, you put back to number 1. So P load is equal to the slope of generator 1 times P at no load minus frequency at no load minus frequency of the system. Frequency here minus frequency here. Meanwhile, for power from your G2 is the slope curve times frequency at no load here minus frequency of the system at this point. So this is the amount of P load delivered or absorbed from the system. Delivered to the load or absorbed from the system. So you can use this equation to find out the amount or the values of the load, P load absorbed from the system or P supplied by the generator. So from the equation, you can see that the system frequency is a function of both generator mechanical governors and also due to the no load frequencies. So the P load depend on the slope and also the frequency. And the slope and the no load frequency. And also the power draw from the generator dependent or relies on how the other generator operated. Means that if the slope is lower here, so means that we cannot draw more from this generator. Instead, the amount only at this value. If the slope is higher, so at this point of frequency system, so we can supply more. Let's supply more. So this is the power amount that we can supply to the load. Okay, means that we have to adjust this roof and house diagram here up or down, such that the sharing will be equal or unequal. You can control from the connected generator. This is example for 2 generator in parallel. Let's say we have 3 generators, so we have to overlap the. Let's say we have G1 here, G2, another one with G3, so we have to overlap over here. And G3, G4 on the same diagram. Or we can put at the side but with the same scale. Okay. Then when we change the load power, just now we fix the frequency. Now if we change the load power, or the load will draw more power or less power from the system, what will happen? With constant generator, no load speed or frequency, means that this roof is static over here. No load speed is fixed. We put a pivot over here, pivot here. No load speed is static, so the roof is stable or is fixed here. What happens if we change the load? Means that from low load here to high load, and low power into high power. Just now we have maybe 100 kilowatt. Now we have maybe 150 kilowatt. So this is 100 kilowatt. Increase to 150 kilowatt. 50 kilowatt. So instead of 100 just now, increase into 150. What happens that we shall have a same frequency which is decreased, and to accomplish the requirement of the load, the level of frequency chilling here will decrease from up to low. So we have another level of frequency over here. Means that we are able to supply the load, but the frequency of the system already goes down, already decreased. So it will affect the system frequency. Same goes to the load when we decrease from 100 kilowatt. So we take out the load 50 kilowatt. So instead of the frequency decrease, the frequency now will be increased. It will increase due to the light load. Instead, the area will be thinner. So the curve, the ceiling or the shielding of the frequency level here will be increased. Paham? So with a constant, so we still look at the P. With a constant generator, no load speed here, constant. When we change the load, the effect will take place on the system frequency. So it means that the frequency system here will decrease or increase. Decrease or increase. So by changing the load, frequency will increase by the amount of same formula you can use. So when we change the frequency, the load, increase the load, frequency will reduce. If we reduce the load, so the frequency will increase. So that's the vice versa of the scenario. So we have to take a look on the power, frequency. So with constant frequency, if we set the frequency at constant, both frequency no load and full load must be adjusted in order to maintain the balanced power between generator 1 and 2. Means that if we have a over here, frequency real power characteristic. Okay, means that if we have a balanced power, you can see here the amount of sharing power here and the amount of sharing power here. So here is half, So if you want to maintain half and half power sharing, let's say we are delivering 100 kilowatt. So it means that this portion is delivering 50 kilowatt. This portion is also 50 kilowatt. When we increase the power demand, let's say into 200 kilowatt, so we want to make sure that both are supplying at the same amount, equal amount, 100 kilowatt as well. So what we have to do is that we have to shift, and we have to shift the overall roof here upward at the same rate. You can see just now at this level, now we have to shift upward, such that the curve or the space below the roof, we have equal area. We have an equal area. So this one supply 100 kilowatt, this also supply 100 kilowatt. So the whole roof have to be uplifted. So means that both F and L and F full L have to be adjusted to maintain the balance of the power sharing between the two generators. Okay, in terms of calculation, constant system frequency, we adjust F no load and F full load. So the amount of F no load and F full load, new no load full load of the system to be adjusted when we increase the load demand. Okay, with the constant load power also, the constant load power, system frequency can still be adjusted by controlling the generator, control the both generator or one of generator alone. We can control both or one. Both frequency at no load and frequency at full load to be adjusted to control the system frequency and maintain the power balance between the generator. So we can adjust both of it, or we can adjust only one generator. So means that either roof kiri ataupun kanan untuk control in terms of their power sharing. So this is a repetition of the previous slide. Means that let's say we need to control in equal, so we have to raise both sides. But if we want to set, maybe this one is 70%, meanwhile this one is 30%, so we just adjust one side. Another side we fix, another side we raise or we reduce. So we are able to control in terms of their portion of power sharing. So same goes to the frequency here. System frequency can still be adjusted by controlling one of the generator. Another one we fix it. If we change both power balance, so means that we are able to control in terms of their power sharing as well by controlling either one of the frequency. So the payload, let's say we have here 50%, 50% here. We want to increase or reduce. Maybe we want to make it as 70% and 30%. So it's by adjusting the roof here. We adjust the whole roof over here. This one we fix. This one only we raise or reduce. So we are able to adjust the power balance or power sharing between the G1 and G2. Okay, for example, I will discuss later. 4 o'clock already. I will upload inshallah with the previous example. So any questions so far from your side? Ke semua dah tidur dah?
Tak ada, sir.
Bagus. Okey, bagus. Ada soalan?